Hi, this is Randy White. Today I'd like to show you an example de-embedding with a USB 3 signal. Here in this example we have a USB 3 drive connected to a fixture. Out of this fixture we take both the positive and the negative complementary signals and run them through different cables. One cable on the positive side is going through a short 20 centimeter cable. On the negative side it's going through a longer 2-meter cable. Let's de-embed both and compare results to see how much improvement we get with the de-embedding function on the RTP oscilloscope. So as you can see on the screen here, we have channel 1 up top, which we're triggering on. Channel 2 is also displayed on the bottom, but we can tell that there's some 8 to 10 nanosecond delay between the output of channel 2 and channel 1. So de-embedding in theory should correct this delay, and we can test this very quickly by turning on the de-embedding function for channel 2. Of all the components that are available here, cables, adapters, fixtures, etc., I'm going to choose cable because that's what we have connected and that's what we're comparing. So I'll choose for this cable example, this is our long 2-meter cable, and just to make sure, I'm going to look at the response, and as expected, long cable has more than 6 dB loss attenuation out to the full bandwidth of this scope. So go ahead, that looks okay, so I'll go ahead and turn this on, go back to our main view, turn on real-time de-embedding because I want the fast update rate on the RTP. And now I enable the overall de-embedding state for channel 2. And the de-embedding filter is being calculated. We'll turn this off. And you can see that channel 2 is indeed higher in amplitude, but it appears we have a problem. Channel 1 is not aligned with channel 2. They're close, but not quite the same. Well, if you look at the setup, there is one minor detail. Channel 1 also has some delay through the cable itself, even though it's short. So once we de-embed that cable, we expect both waveforms to be time aligned. So now I'll go back to channel 1, add our cable. Of course, this is the short 20 centimeter cable. If I look at the loss, this is about 1.25 dB out to the bandwidth compared to the 6 dB loss of the long cable. So turn this on and turn on real-time de-embedding as well. Now I'll go ahead and close this window. And now I compare both channel 1 and channel 2, and I can see that the trigger of channel 1 aligns with the same point in time as channel 2. So this confirms that de-embedding does not only remove compensation, but also aligns the amplitude for each channel. So let's go ahead and take a closer look. If we look at the eye diagram for channel 2 before de-embedding, we can see the attenuation of this long cable results in a lower amplitude, specifically lower eye height. If I turn this back on, I expect channel 2 eye height to match channel 1, and indeed in this case it does. So this was a quick, easy to follow example showing de-embedding of a high-speed digital signal, in this case a USB 3 device, going through a long cable, and after de-embedding we compare that the eye height result matches our short cable de-embedded result.